Welcome everyone again. This is the first session of today. The title of this session is The Next Decade of Black Holes. We will have three speakers, Sasha Philippov. This will be followed by the talk by Andrew Chael and George Wong. So each talk is 25 minutes plus 5 minutes for discussion. So we will start with Sasha Philippov, who will tell us about his kinetic plasma physics near the event horizon simulations. Go ahead, Sasha.
Thanks, Monica, and thanks the organizers for inviting me here. I'm going to tell briefly about the work that we've been doing trying to incorporate kinetic physics into understanding the plasma dynamics near the event horizon. This had been the work with Kyle Parfit, Benoit Cerruti, and Benjamin Quincant for the PIC part, and the rest of the people that some of you already heard in MHD talks. So I'll just briefly remind you some facts that we heard last time, probably in Elliot's talk, is that in both cases, in Sagittarius A star and in M87, the plasma flow around those black holes is really collisionless. What this really means is that the mean free path for Coulomb collisions between the charged particles is actually much larger than the system size in both of the systems. So MHD is really not applicable formally. However, there is a strong magnetic field which confines the particles in the direction across the magnetic field. So the plasma is what we call magnetized, but comparing to what you call magnetized in MHD, here we really mean that the Larmor radius of the particles is much smaller than the characteristic scales in the system. So in this language, MHD is a theory of a perfectly magnetized plasma. The Larmor radius of the fluid is really zero. So what I'm mainly going to focus is not the accretion flow because it's a much more complicated problem for plasma physics, but on what can happen inside the jet, how the plasma can populate the field lines in the jet, and also talk about the recent advancement that we made with MHD, trying to understand the flares from the systems. So just briefly remind you, in case someone is not familiar with kinetic description of the plasma. So in principle, the most fundamental description of the system is just to follow every particle in the system. So you would have tremendous amount of information. You would have each coordinate of the particle, each momentum of the particle. But this is really incomprehensible for any realistic system, for any plasma in the universe or in the lab. This brings too much information on the table. So the major advancement in kinetic theory was made back in 1930s and 50s when people reduced the equation for distribution function which describes every particle to the distribution function which describes only one particle. So this is a well-known equation called the Vlasov equation. This describes the evolution of the distribution function, which is a function of only one coordinate and one particle. The price of this reduction is what we call a collisional integral, the term that stands on the right-hand side. This describes the binary processes between the two particles. So luckily, in most of the astrophysical systems, the collisions are so rare that you can even give up on this term, and then you end up pretty much with a continuity equation of a distribution function in the phase space. So this just describes that the flow of the distribution function in the phase space is described by the velocity and the force, and this force is the Lorentz force given by the electric field and the magnetic field in the system, and this electric field and the magnetic field is described by the Maxwell's equations. So the closure of these equations happens through the currents and charge densities. They're calculated through the integrals of the distribution function. The whole charge density is an integral of the distribution function times the charge of the species, and the current is the first moment of the distribution function. So in principle, this is a complete theory that you could in principle apply to any astrophysical plasma and get the answer. So of course, there is no free lunch, and I'm going to discuss the limitations of this. But here I just want to briefly contrast these two approaches, the kinetic and the fluid approach, for this particular case that we're all excited about, the plasma flows around black holes. So the first assumption that the fluid dynamics takes is that the plasma is really quasi-neutral. the charge density of the plasma is much less than the net density of the plasma in the system. This is a very good approximation in the disk, but depending on the system and what you assume about the radiation field, you can get into situations where the charge density inside the jet would actually be comparable to the density of the plasma. So this assumption can easily break inside the jet, at least in the vanilla type MAD type accretion flow. So the second assumption that the MHD takes is that the plasma is highly collisional and has a single temperature, and it obeys a Maxwellian distribution. So Maxwellian distribution of a single temperature is a nice solution of the Vlasov equations, but it's not what typically happens with collisionless plasma. So collisionless plasma typically develops power loss, the plasma becomes non-Maxwellian, and the electrons and the ions don't have to have the same temperature. So this would be deviations from these assumptions, and this is applicable pretty much everywhere, both inside the disk and the jet. It's hard to really assume that anything is Maxwellian, especially when magnetic fields are important. The third assumption is that the plasma is an ideal conductor. This tells that the electric field in the frame of the conductor is zero, meaning that if you jump into a frame moving with the conductor, the electric field would vanish. This is a natural assumption because if there would be this electric field in the frame of the conductor, you would stream opposite charges in different directions and induce voltages. So what plasma typically does, it wants to screen the electric field in the frame of the conductor. Once it's screened in the lab frame, you get this nice equation in flat spacetime, electric field plus V cross B is zero. So the drawback is that this doesn't really describe much of the acceleration of the particles, at least inside the jet. And in the case when the charge density is not negligible inside the jet, this assumption is actually wrong. So MHD is basically a theory which takes us three assumptions and computes the moments of the kinetic equations and formulates equations for these new variables, mass density, temperature, velocity, and the magnetic field. And typically it's a very good approximation for large scale dynamics. But if you want to model particle acceleration or radiation, it's really hard actually to rely on MHD. So this is a theoretical cartoon that we are all thinking about. There is an accretion flow somewhere at the midplane. There is a black hole. This plasma accretes. It brings magnetic field with it. Magnetic field gets dragged on the black hole. The black hole is spinning. And if it would be sitting in vacuum, there would be tremendous voltage on this field lines inside the jet. The space-time of the black hole rotates with it. And similar to the Faraday disk, which is a perfect conductor, the spinning magnet induces voltages on this polar field lines. And some of the voltage starts to accelerate spray charges that you could sprinkle inside the jet. So this is what has been postulated in Roger Blanford and Znaik's 1977 paper, is that you would get a vacuum breakdown because you would throw some seed charges in this vacuum electric field. They would charge separate, electrons would go one way, positrons would go another way. They would scatter the soft photons from the disk. The soft photons would annihilate on the upscattered photons by accelerated particles, and this would get to the pair avalanche. So this is what we call a pair discharge. If the radiation flux from the disk and from the boundary is very low, as we would expect in case of Sagittarius and M87, then a lot of pair production is actually going to happen on the jet field lines. This would be facilitated by a process of formation of what we call gaps, where the vacuum regions develop and accelerate particles. These particles upscatter photons, and this creates plasma. So why this is important is that because in this vanilla type picture of accretion, the field lines in the jet are magnetically encapsulated from the accretion flow. So since the plasma is only streaming along magnetic field lines, it's actually impossible to get any plasma from here on the jet field line. So inside the simulation, it manifests itself as that the jet is sitting on what's called the density floor, which means that there is a constant source of injection of plasma on those field lines, which sustains the flow. So in reality, this has to be sustained somehow, either most likely with pair production. And there are two channels for pair production. One channel is what I described, is that when there are soft photons from the accretion flow being upscattered by accelerated particles on jet field lines and then get reabsorbed by the same photons from the disk. This leads to a double photon pair production and the pair outflow. Or there would be a hidden MEV kind of flux, which would annihilate directly inside the jet and pretty much provide this outflow without this process of pair discharge. So I guess this is what George Wong gonna talk about in his third talk. What I'm gonna caution everyone is that those type of models actually rely heavily on the electron temperature in the jet boundary. Since we don't really know the electron temperature from the MHD simulations, I'm gonna take a conservative approach and say that this is a radiationally inefficient flow and just simply doesn't provide enough radiation to provide pair production inside the jet funnel. So to solve this problem, we came up with an extension of a traditional approach to model plasma physics in flat spacetime, the particle and cell method. We extended it to general relativity, and what we're really doing is that we have a computational grid, as everyone is doing. So we have a grid on which the electromagnetic field is defined, and then through this grid we have individual particles flying around and feeling the Maxwell force and the gravitational force. So basically, we're advancing a collection of particles. We are collecting charges and currents with them and feedbacking them into Maxwell's equations, which provide self-consistent electromagnetic fields. So this is how the typical loop of a calculation looks like. We have initial distribution of charges. We know the charges and currents. We can integrate the equations of motion of the particles with given electromagnetic fields. We can redefine the force acting on each particles, and then do this every time step. So we collect the currents and then feed them back into Maxwell's equations. This is, of course, the most first principle description that you can imagine. The price is that you have to resolve microscopic scale. So in this problems, the microscopic scales are the plasma skin depth, so the C divided by the plasma frequency, the scale at which most of the plasma processes actually happen. For example, the screening of the electric field that I described earlier would happen on the scale of the plasma skin depth. And the second is the Larmor radius, that the particles gyrate around the uniform magnetic field with a circle-like trajectory. And the size of the circle is called the Larmor radius. So inside the jet, this Larmor radius is pretty much irrelevant. The magnetization is so large is that the Larmor radius is pretty irrelevant. So in what comes out next, I would just not worry about the Larmor radius whatsoever. The particles just go as beds on the wire. They just slide along the magnetic field and do the drifts. So the Larmor radius is irrelevant. So the skin depth is very relevant. It's much smaller than the size of the black hole. However, certain problems, we just know what happens in the regime when the skin depth becomes much smaller than the microscopic size. And I'll try to go problem by problem in this case. So this is the first application of this code that we did. We tried to simulate what's called a Wald solution. We hooked up a uniform magnetic field on a spinning black hole, and the simulation starts in vacuum. The black hole in vacuum has this peculiar property that it expels all the magnetic flux from it, so it's a perfect superconductor. However, once you start sprinkling plasma, all the field lines get dragged and to the event horizon, and in the steady state, all the field lines that pass through the ergosphere also pass through the event horizon. So this is what's called the Wald solution. There is a nice pointing flux along open magnetic field lines. So this is the Blanford's-Naik process happening with the first principle kinetic simulations. There is a current flowing along those field lines. There is a toroidal magnetic field. There is a pointing flux E cross B coming outside of the black hole. The price of this pointing outflow is the current sheet in the equatorial plane. So in the equatorial plane, you actually have total asymmetry between the field line components, both the field line in the plane, which is shown as this black surfaces, both the spheroidal field and toroidal field, the field component out of plane, reconnect inside this equatorial region. But what we mean by reconnecting is that when you bring two opposite magnetic field lines together, they try to annihilate themselves, and they do it by process of changing their topology. So the field line that was going up actually connects with the field line which was going down. So this is a cartoon picture for reconnection. as always picked from Wikipedia. So you see what I just described in words. So the field line that enters through the current sheet goes through the current sheet and reconnects on the other side. So there has been tremendous progress in understanding how this process happens. And as far as we are concerned, in a highly magnetized limit, there are certain indications that even in 3D, the reconnection process happens through the formation of what we call plasmoids, the big blobs of plasma and magnetic field, which break this laminar region where you try to annihilate the two magnetic field lines into a bunch of these islands and the regions in between them, which we call X-points. So this brings certain implications that I'm going to describe next. But for now, I'm just going to tell you that reconnection inside the current sheet brings a new form of energy extraction from the black hole. On top of the Poynting flux on the open field lines, you can start having what we call a Penrose-like process of energy extraction. And this works because there is electric field inside the current sheet that works as a Penrose agent. You have an electron-positron pair, which this electric field basically splits, sending electron one way and positron in the other way. And one of them gets into a trajectory which has a negative energy as seen by observer at infinity. This particle then falls out on the black hole, and the other particle, which has larger energy, escapes. So this is similar to the Penrose process, just that he's thinking about how the pair of particles is splitted happens here through the electric field. So I'll just not going to focus on this, but you can measure all of this self-consistently in the simulation. You can measure the flux of the particles with negative energy and find out that in a typical simulation, it would get to something like 10 or 20%. So this is a particle contribution to the energy extraction in this particular simulation. So let's get back to this process of discharge. We are now looking at just the jet field lines, and we are trying to simulate how this process of pair creation actually happens. So again, the simulation starts in vacuum. There are some simple charges available in the system. The rotation of the black hole drives electric field, and this accelerated particles start to upscatter the photons from the disk, which in this case is postulated. So we assume a very simplistic monoenergetic radiation field of soft photons, and the soft photons are self-consistently upscattered by accelerated particles. They produce high energy photons that are self-consistently tracked inside the simulation. So these photons then annihilate on the soft photons and provide electron-positron pairs. So what we find in the simulations is that this pair production process is very non-stationary. You start to create this vacuum-like region with no particles, but then the particles are accelerated, they produce photons, the photons annihilate, and you get pair plasma. So the pair plasma screens the electric field that you get in the first place, and this process stops for a while. You need to wait until this plasma evacuates from the vacuum-like region and get the machinery work again. So this is what you see on the right panel. This is the density of the plasma. You see individual sort of clouds escaping from the region near the event horizon. So this is this intrinsic non-stationarity of the discharge process. We are pretty certain that even if you scale this problem down to the realistic scales, there will be still this huge time dependency happening in the system. This is reminiscent of how this happens in neutron stars and pulsars and magnetars, by the way. This process has been postulated to potentially drive large TeV flares from 87. We find this problematic a bit because the TeV flares from 87 lead to something like 1% of the jet power. These simulations do show 1% of the jet power in TeVs. However, if you try to rescale them to realistic parameters, the TeV flux would be at least 10 or maybe more pessimistically even 100 times lower. So realistically, I think the TeV flares cannot happen in quiescent type gap where you get the production of pairs sort of in quiescence. So this is where 3D MHD comes in. Could we sort of think of large scale variations in the flow which would violate this quiescent type picture? And it turns out it can. So this is a simulation of a vanilla type magnetically arrested flow conducted by Bart, Matthew Lisk, and Kushek, but done at a resolution about 10 times larger than the simulations that have been done before. So what they found is that the matte flow is highly variable, and eventually it undergoes the events which we call flux eruptions. So the rapid drops of the magnetic flux from the black hole, which are accompanied by the dip in the mass accretion rate. So what happens is that you hook up so much magnetic field on the black hole that the accretion is really stopped, at least in certain latitudes. So it's not an axisymmetric picture, but on certain azimuthal angles, you don't see much accretion happening. So this is where reconnection comes in. The magnetic field right down near the black hole starts to reconnect inside this equatorial region, and this is how the magnetic flux can escape the black hole. So these flares are very interesting in terms of finding out how the radiation flux from the disk can actually affect the production of the charges on the jet field lines. So this is just a zoom in to show you that reconnection is actually happening. There are oppositely oriented magnetic field lines in the jet touching in this equatorial region. The plasma in this very thin flow gets very hot, and it's unsurprising because the density here is just sitting on the density floor. The density of the disk, which is much higher, is just completely separated from this region. The high density is sitting on the outskirts, and this very low density region is very hot because it tries to sustain the jet against the collapse. So this current sheet has to provide pressure balance between the hot plasma in the current sheet and then the highly magnetized jet. So this is where reconnection happens. And Bart described more in his talk yesterday. So the time between flares is something like 1,000 horizon light crossing times. It's roughly a year for M87. So it could be interesting if there is an interesting observational signature, which we think it is. And I invite you all to come to Kushik's talk in the breakout sessions in the afternoon, that if new generation ngEHT can actually sample both the quiescent time when there is a steady accretion on the black hole and this intermittent variability with reconnection, which we call a flare. So if both of these periods can be sampled by observations and there is a nice observational signature, then we could actually even measure the reconnection rate, because the rate at which the magnetic flux is reconnecting is determining how much this flare is actually happening. So this is where I argue that for certain problems, even the large scale description of the system is wrong if you do MagnetoHydroDynamics. So this is a simple case when I just hooked a magnetic field on the black hole, and I hooked up a magnetic field which is dipolar, which is not actually sustaining for a long time. So this is relevant, for example, if you collapse a neutron star onto a black hole, and initially you'll get a rotating black hole with a dipolar magnetic field. So the field lines will do.
Excuse me, 1 more minute.
Yes, I'll finish in 1 minute. So the field lines would open up, and you'll find out a nice current sheet in the equatorial plane. Ashley Bransgrove, a student at Columbia, did very nice analysis of both GRPIC simulations and resistive MHD simulations. And what we find is that the rate at which you decline the magnetic flux on the horizon is actually different between MHD and PIC. And this is fundamentally true because the magnetic reconnection rate is different in collisionless plasma and in resistive MHD. And if anyone wonders why, I can answer in the question section. So I'm just going to show you the last slide. This is my thinking. It's a very speculative thinking about what can heat up the plasma in, for example, the jet boundary system, jet boundary layer. So in maths, this region of the flow is having some sort of low plasma beta. So we think that the energy is mostly stored in the magnetic field. So if the energy is stored in the magnetic field, it's sort of healthy to think that maybe the source of energization and heating is magnetic reconnection. With predoctoral student Sasha Chernoglazov, we tried to simulate this in MHD and asked the question whether the current sheets that you actually find both in large-scale simulations of accretion and in localized simulations of turbulence are actually reconnecting. And the answer is yes, they're reconnecting. You have to have tremendous resolution. So for magnetic Reynolds number of 10 to the 6, to converge it in 2 dimensions, you need 64,000 square grid cells. But you do convincingly find that you find large scale intermittently forming current sheets, which are reprocessing a lot of the plasma. and they are reconnecting. And by the statement that they are reconnecting, I mean that there are plasmoid unstable, there are full plasmoid chains happening, and the field line topology is changing inside this current sheets. This also happens in 3D. The larger scale current sheets are unstable. You see nice plasmoids happening in biggest current sheets. I think I'll just stop here by saying that reconnection, I think, is a likely candidate for hitting and energizing plasma in low beta regions of the accretion flow. Thanks so much.
Thank you, Sasha, for excellent talk. There are two questions in chat, but maybe we will start with Silke. You are raising hands. Do you have a question?
Yeah, thanks a lot for this very nice talk. Intuitively, I'm very convinced about this reconnection, but I would like to know, how do you connect the reconnection to the scales of AGN jets? Is that possible? You mentioned that there are problems when going to larger scales. So I'm always standing in front of the question, how do I get the reconnection scenario into the AGN jet physics? Is there a way to proceed?
This is a very broad question. I could give another an hour talk about this.
Oh yes, please.
But I think you know what you have to understand is that although you're forming this large scale structures, which are macroscopic, they're horizon type long, where the action is actually happening for a kinetic plasma is microscopic.
Yep.
So, for example, if in localized simulations of the reconnection, the reconnection would actually happening down on the skin depth region. This is where you form this nicely small X points where the field lines are actually converging and breaking apart into plasmoids. So inside the flow, the reconnection would happening on very small scales. So how to connect to observations has been very problematic for me and will be problematic for next 10 years and maybe more. This situation where you form a very large scale current sheet, for example, like in this magnetically arrested state, is sort of easier. We think that there is a very sort of extended large scale current sheet. So this is a situation known as a solar flare. So in the solar flare, the size of the current sheet is really macroscopic. It's very thin, of course, because it collapses by the magnetic pressure from the jet, but it's macroscopic in a sense. So I think I can just apply my local simulation of kinetic reconnection and get the answer. It's all very different for current sheets inside the turbulence. So what I showed you here is that these are like very large current sheets. Their size is, again, sort of a quarter of my simulation box. Are they the most important for heating energization? I think the honest answer is that we don't know, because the most advanced theory actually predicts that if you go up to magnetic Reynolds number of 10 to the 14, which is actually more relevant for astrophysics, you can start to get reconnection all over the place, because the magnetic eddies which you will form in this turbulence would be elongated in a plane perpendicular to the magnetic field, and every eddy of a scale smaller than a certain scale would start reconnecting by itself. So this would create more like a uniform sea of dissipation inside this turbulent box, which would be very different from what we can simulate and would be able to simulate in the near future. So I think it all boils down to what is the problem, what we want to know from this problem, and what is the signature that we want to model.
Okay, many thanks.
Yes, so unfortunately, we don't have much time for questions. We are already over the time. And so
Can we get Avery's question at least?
Okay, go ahead. Maybe quick one, Avery.
Thank you. Yeah, so this spark gap behavior, this non-stationary behavior, was something that Sasha and I also saw was likely to happen. But it looks like even in your simulations that it is happening over a time scale that is relatively short. And so if you imagine the gain region when you're integrating up the flux for something like an ngEHT image, it's actually averaging out all of these sparks.
I think it's right. The variability is lower than it's seen. So I have to mention that there are also one-dimensional simulations of this, which probe at least better scale separation between the skin depths and the macroscopic scale, the variability is enhanced in one-dimensional simulation. So here, what we see is more like one-tenth or even smaller of the horizon size compared to the 1D simulations, which have variability on more than RG over C. So I don't think it's relevant for the EHT observations, also because I don't think you can actually form this much plasma inside those gaps. So there is, of course, a post-gap cascade, which we're not modeling, but at least down to the scales, the multiplicity is pretty low. It's more like 10 times the Goldberg-Julian. So I think it might be relevant for high energy observations, but not for EHT-like scenarios. So that's
exactly.
My
yes, thank you very much, Sasha. There are more actually questions also on the chat, also related to high energy neutrinos and so on. If you could answer those, that would be great. And everyone else, please ask more questions on Slack.
Thanks, everyone.
Yes. Thank you very much, Sasha, again. And now it's time to move on to our next speaker is Andrew Chael from Princeton University, who will tell us the other side of the story, GRMHD simulations, and specifically on radiative GRMHD simulations. Go ahead, Andrew.
Hi, can you hear me?
Yes.
Yeah. Okay, great. Yeah, so thank you for having me. Today I'm going to talk about some, at this point, simulations that are several years old, but that we're still getting new insights from. So we're recapping some old results and then discussing some projects in progress. And in particular, we're motivated by trying to understand what these simulations can tell us about what the ngEHT might see in M87. So sorry, Sagittarius Star fans, this is a M87 focused talk, but I hope we'll have some insights that might apply in Sagittarius Star as well. And in particular, what the ngEHT might learn about the extended jet in the near horizon region and their interconnection in these simulations. And I think both of these are particularly important, as we've heard from talks throughout the week, for the ngEHT to address. We know the M87 black hole image that we produced with the EHT is situated within this extragalactic jet. It goes out to large scales. Simulations tell us something about how this jet is formed. We know from Sasha's talk yesterday, for example, the jets seem to be universal in a lot of these simulations. We use the jet power constraint in paper 5, but there's still much to learn, I think, in terms of what the simulation conditions are that produce these jets, and and how they're formed. And we can approach this both from a new generation of simulations, and I hope with ngEHT observations in the next decade. So in the first part of the talk, I'll just discuss these simulations, which were published already almost 2 years ago now, with radiation and heating. Asking the question, what determines the images we see in simulations, and how might we do better than standard GRMHD? So by now in the conference, I hope you have this picture of how GRMHD simulations and relativistic ray tracing work, this sort of primary analysis tool that the EHT uses as we solve the coupled equations of fluid dynamics and space and magnetic field in the black hole spacetime in these 3D GRMHD simulations, and then ray trace their emission to produce movies and pictures of the black hole images that the EHT sees at 2-3 gigahertz. And in terms of determining what the fundamental features of these images are, we have things that, again, we've talked about all week, such as the magnetic field structure. Is the magnetic field in this standard turbulent field evolution state where the magnetic fields are weak and turbulence allows for accretion, or are they in this magnetically arrested disk state where fields become coherent and strong and push back against the accretion flow? In general, we have the insight that Blanford-Deniak jet power is proportional to the magnetic flux in the black hole. So you might expect this MAD scenario to be a natural one to explain powerful jets, for example. We have the question of where the emission comes from. We know from the EHT paper 5 models that in almost all the models, the emission region is within 5 gravitational radii of the black hole, so subject to very strong gravitational lensing effects. Inside, with emission coming from inside this region of photon orbits, for example, as in this picture from paper 5. But the exact shape of the emission region differs from simulation to simulation. Is it something that's somewhat spherically symmetric? Is it something that's lights up along the jet sheath? Is it something that is more concentrated in the equatorial plane, for example? And then critically, for this work, what is the distribution of the emitting electrons in the simulation? So we just had a great talk on how we can look at the electron distribution in the very first principles, way. We know that in these flows, the the coupling between ions and electrons is inefficient, and so we don't expect the electron temperature generally to equal the ion temperature. This temperature is sensitive to radiative cooling and microscale plasma heating processes, which will both play a role in determining what the temperature of the electrons is, and ultimately, and their distribution function if they're able to maintain non-thermal distributions. So all these effects are important in determining the images we get from simulations that we then want to compare to EHT and ngEHT data. And typically the way that this comparison is done is we run GRMHD simulations that don't evolve for separate electron temperatures, which don't include the effects of radiation, and then try to simulate those effects by assigning an ion to electron temperature ratio in post-processing manually. This is what was done in paper 5. For example, we have this image library of many thousands of simulation snapshots from 43 different simulations that use one family of post-processing temperature prescriptions. This temperature prescription originally came from Monica, and it was designed to simulate the effects of one particular type of plasma heating scenario. But all this is done again in post-processing. An alternative thing that we can do is use radiative GRMHD to investigate both the effects of radiation on the plasma's energy momentum and the effects of plasma heating on the electron temperature. And so why would the radiation part be important? Well, we know for M87 that the accretion rate is high enough that the radiative feedback might start to become important. So for example, EHT paper 5, also Ryan et al. 2018, also my papers found that in some reasonable models of M87, you see radiative efficiencies of about 1%. So, not exactly entirely radiatively inefficient anymore. And in some of these simulations, here on the right, you see the ratio of radiation pressure to gas pressure can approach unity, depending on which plasma heating model you use. So we might expect that radiation has a significant role to play in determining both the electron temperature and also the gas energy momentum in these systems, in M87 at least. So radiative GRMHD simulations take the next step beyond standard GRMHD simulations to include this radiative cooling and feedback on the energy momentum. There are now many different codes and methods to do this with increasing degrees of sophistication. So I think we're really in a point now where we can start comparing these codes, start understanding which ones work and which ones are necessary to investigate these systems. Another thing that the radiative GRMHD makes it natural to do is to include subgrid models for electron heating in the simulations. So for instance, this is what we call two-temperature GRMHD, where we evolve separately electrons and ion temperatures, not assigning them after the fact in the simulation, in post-processing the simulation, but evolving them along with the other simulation variables by using an underlying plasma heating model to source the heating in the simulation. So this allows us to, like I said, incorporate different heating models inspired by plasma physics simulations on microscale. So some examples of this are reconnection that we talked about in the last talk, Landau damping processes, Fermi type acceleration. All of these can take a model from our favorite plasma physicist and put it into these large scale simulations and see what it gets out. And we can see just from this example of two Sagittarius star simulations on the right that this can have a large effect. The type of heating that we apply can have a large effect on the results, where this Landau damping type simulation gives a much more jet dominated image of 43 gigahertz as opposed to a reconnection type simulation, which produces a much more disky image. Now, a major limitation of this whole enterprise is that the space of heating models, I think, is, at least as someone outside of the plasma physics world, seems to be pretty currently unconstrained. So, it's not like we have a best bet heating model that we can plug into these simulations and say, aha, I know exactly what is going on in M87 now. And these are a lot more expensive to run than just applying many different heating models in post-processing. But I think that by running a few of them, we at least gain some insight into where our post-processing heating models go wrong and or where we might need to go further. And so, for example, here's an image that compares what we get from one of these radiative simulations if we apply a post-processing model, sort of a best bet post-processing model using the EHT paper 5 Moskva-Brodska 16 prescription. Here on the left, where we see this model in post-processing has a very sharp transition between the temperature ratio in the funnel region magnetically dominated and the disk, and then it's relatively constant in both those regions. But in the actual simulation, which evolves the temperature ratio self-consistently with an underlying plasma heating model, we see a much more complicated structure. We see, for instance, that the temperature ratio isn't unity in the jet. The electrons are still cooler than the ions in the jet, and there's a much more complicated structure in the disk as well. And so, one thing we might want to do is to create a library of these radiative simulations, analogous to the M87 library. This is something that I've done the last year, so hopefully we'll see some results from that to compare to the GRMHD library from GHD paper 5 sometime soon. But as again, the fundamental issue with this approach is that there's no freedom to adjust the accretion rate after the fact, and the space of heating models is pretty unconstrained. So this isn't a silver bullet by any means for understanding these, for understanding M87, but I think it's a way that we can go beyond our current simulations and test them and see what assumptions we're making are hold and which are violated when we incorporate some of this extra physics, even if we don't understand exactly what those models should be. Okay, so in the next part of the talk, I'll talk about jets from these simulations of M87 and how similar are these jets to what we see in M87, and what features of them might we observe with the ngEHT. So the simulations I'm talking about were published in this paper in 2019. There are two MAD type simulations of M87, one using a turbulent heating model for sourcing the electron heating, and one using a model derived from that magnetic reconnection simulations. These were performed using the Coral code. So all the simulations I talked about for the rest of the talk will be from this set of two. But again, hopefully we have new ones coming relatively soon that span a much larger parameter space. So one of the features we see, at 230 gigahertz, images from these simulations look very similar to what we see in the EHT simulation library, with emission concentrated near the photon ring. If we sort of zoom out and look at multiple millimeter wavelengths in a log scale, we see that these simulations also both launch very nice wide jets to large scales. And the wide opening angles of the jet get larger with increasing frequency. And we can start to compare these jets that we observe at 43, 83, and 230 gigahertz in the simulations with the jet that we observe from M87. So these jets, here's a movie of them at 43 gigahertz. These simulations, are not evolved for super long in this business. They're 16,000 gravitational times. So we could, by evolving them further, extend them even further. But even in just that time, they produce converged jets out to about a parsec, or really arc second, at a reasonable SCD down to about a centimeter. So the first thing we can do is just compare these to what we see from VLBI at 43 gigahertz, for example. And here we see on the left here the image from the VLBA from VLBI Walker of the jet at 43 gigahertz. And one thing that's strikingly apparent about it is this very wide opening angle of this jet. This isn't a narrow pencil thin jet at the base, but it's something that has this wide opening angle about 55 degrees. And just sort of plopping that 55-degree angle down on the simulations, we actually see that they do a fairly good job of reproducing something that wide. And this is something that you don't see in the same type simulation where the fields are not dynamically important near the black hole. Those tend to produce jets that are much thinner, that don't show this wide open angle. So this MAD type simulation sort of naturally explains this wide opening angle. In addition, we can look at the powers from these jets as a way of sort of distinguishing between these two heating models. One thing we notice is that the mechanical jet power in the reconnection heating model is consistent with the range of jet powers measured from M87, whereas the turbulent heating model is too weak. We interpret this to be the case because the turbulent heating model has too much energy going into radiation. This turbulent heating model produces way too much very hot electrons in the funnel. And I wouldn't say this is as strong of a conclusion as the general trend of the jet opening angle to be wide in both simulations, but it's an interesting way of starting to see if we can constrain the space of heating models using these observations. And I would also mention that neither jet is as brightened as we see in the VLBI images. So we're certainly not explaining all the features of the image, but this fundamental feature of the wide opening angle is something that we can now reduce up to down to sort of centimeter type frequencies in in M87. So this is of course at 43 gigahertz, but at at the issue 2017 image, we don't see this extended jet, but we expect it to be there. And so on the left here is the simulation of the jet base at 230 gigahertz, where you see this EHT type image of the innermost accretion flow is embedded within this larger, dimmer, less bright extended jet. And with EHT 2017 dynamic range, if we try to produce the image reconstruction of this jet, you've probably seen this, this image before during this conference, but if you try to produce an image reconstruction with EHT 2017 coverage, we just don't have the dynamic range necessary to observe this extended jet. We can capture the feature around the emission ring, the brightest part of the image, relatively well and resolve this ring, but we can't image the jet out to large scales. With the ngEHT, with the increased dynamic range, one thing we hope to be able to do is just to be able to observe this jet and to connect its evolution with the evolution of the accretion flow around the black hole. So two features of the ngEHT are going to be really nice. Going to 345 gigahertz will increase the resolution of these images, and the increased UV filling will enhance the dynamic range and allow us to produce these nice jet images. And just so we get a sense of, this is a very preliminary ngEHT concept that I've been working with, maybe an optimistic one, but just to get a sense of what the difference is in terms of dynamic range and resolution. This is a comparison of the UV coverages of the two arrays that I use in image reconstructions in this talk. And after working with the ngEHT coverage for a while, I had to sort of do a sanity check to tell myself that this is really what we had in 2017. It's very limited compared to what we might get in the future with ngEHT. We really will fill in this UV plane and maybe understand from high dynamic range observations what's going on in this extended jet region. One other thing we can do with the ngEHT in this project I'm working on now is sort of try to understand the multi-wavelength jet science by looking at images across frequency. And so this is showing two sort of spectral indices between two sets of frequencies resolved in the disk and jet of the black hole. And here on the left, we see the spectral index between 86 and 230 gigahertz. We see a striking difference between the disk emission in the ring close to the photon ring, where we have where the emission is becoming optically thin between these two frequencies. We have a positive spectral index, and the extended jet, where the emission is already optically thin at both frequencies. We have a negative spectral index. Whereas between 230 and 345, the spectral index is more constant everywhere. The whole system is optically thin everywhere. So multi-frequency imaging, capturing the spectral index behavior between pairs of frequencies and its evolution over this whole range of frequencies, can constrain the plasma properties with the spectral information and give us another tool in our toolbox, in addition to things like total intensity imaging and polarization. Just to give a taste of how this works, here's the simulation at 86 gigahertz, 230 gigahertz, and the spectral index map between the two, where you see this difference between the emission right around the black hole and the extended jet. And this is what we get if we use the EHT 2021 coverage and the GMVA image separately. And this is in a gamma color scale, so we're accentuating dim features in the image. And so we can see that, again, the EHT unit 2021 can't resolve the extended jet. And if we try to compare these images directly, we get sort of a mess. It's hard to register them. We image them separately. The 2021 image doesn't image the extended jet structure at all. But if we go to ngEHT, combine it with GMVA, and then use this new imaging method for multi-frequency synthesis that I'm developing using EHT imaging, we're able to combine data from both frequencies, use the beautiful UV cover that we have across this whole space, and constrain jointly the spectral index information as well as the image structure at both frequencies. So something we're able to do is pull out the central depression at 86 gigahertz, as well as image the extended jet structure at 230 gigahertz, and then map the spectral index structure across the full range. So imaging jointly, developing these new imaging algorithms and testing it on these simulations that span a large degree of frequency space is one thing that we can start to use to understand what sort of features the ngEHT might pull out of M87. And then we also have this, we're also able to do this in time. So this is a movie that was prepared by Lindy Blackburn using some of the EHT imaging scripts that we've developed together. And we can see that because we have a full night of observation for every snapshot in these movies of M87, over this sort of 3-year timescale of these simulations, we're able to track, if we were able to observe every single night with the ngEHT, be able to track the connection between the emission right around the black hole horizon with the extended jet in pretty striking detail, and observe things like magnetic filaments propagating outward through the jet at 2.3 GHz. Okay, that was a taste of what we can see about the extended jet from the simulations with the ngEHT. The last part of the talk, I'm going to talk about what we might see on closer in scales near the event horizon. What do these simulations reveal about what the ngEHT might see on horizon scales? So first, just to recap some of the features of the near horizon emission that we've discussed in this conference so far. First is the black hole shadow that we all know and love. Black hole shadow is a set of rays here that from the observer plane end up in the event horizon. The boundary of the shadow is the critical curve. This is a universal feature in simulated images, in particular from those from optically thin spherically symmetric accretion. For example, this image from Ramesh's paper from a couple years ago on the right. Another feature that we see in simulations is these photon rings that were discussed yesterday in the great talk by Alex. So as geodesics wrap around the black hole multiple times, they form a series of images of the emission region that are lensed into increasingly narrow rings as we do more and more wraps. And so these increasingly narrow rings increase in brightness, but decrease in size as we get close to the critical curve. Actually resolving these subrings requires the emission region to be spatially limited. If we have a completely spherically symmetric emission region, such as here on the right, these rings actually all blur into one. We need some sense of a distinct emission region to capture these rings. So a third feature of the near horizon emission that probes the gravitational physics of these systems that we might observe with the ngEHT is actually the central brightness depression, the very central brightness depression of these images, which is actually, in these simulations at least, the outline of the equatorial event horizon in these simulations. So this is a third feature, in addition to the shadow and photon rings, we might hope to observe with the ngEHT. And while it's not a universal feature, like the photon ring, it depends on us having emission that extends down to the event horizon. This is something that the simulations start to point at, something that might be visible with ngEHT. So just to introduce, if not familiar what this image is, we have from this image from Alex's talk yesterday, this picture of if we have emission in the equatorial plane, for instance, geodesics connect us to that emission doing multiple wrappings around the black hole. So we have the direct emission straight from the equatorial plane. We have emission that goes around the backside. We have emission that wraps around one, and this produces a series of rings of increasingly higher order, increasingly narrow in the image plane. And here on the right, we have an image of where we can see photons that execute these different numbers of wraps. So, from most of the plane, we can see emission that comes directly from the equatorial plane. From a narrower region, we can see an n=1 ring, and from an even narrower region, we can see an n=2 ring from emission that has from photons that have gone all the way around the black hole once. But critically,
1 minute.
1 minute. Okay. Critically in the very interior of this region, we have emission that comes. We have a region of the equatorial plane that is punched out by the black hole event horizon, where we can't even reach the equatorial plane once. And this is illustrating this nice picture from this paper by Dokuchev in 2019, where we see this this horizon feature is the lensed image of the geodesics that directly trace the event horizon. So why is this horizon visible in these simulations at all? The reason is because in these simulations, at least, the 230 GHz emissivity is predominantly equatorial. I should say equatorial. It does not truncate at the ISCO, but extends to the horizon. So we have, in this equatorial plane slice, a emission profile that extends all the way to the horizon, not truncating ISCO, predominantly equatorial. So we expect to see a signature of the equatorial event horizon. And also critically, the fluid velocities here are self-declaring. It reduces the redshift of the feature. So in the simulation images, these are time average simulation images to enhance the appearance, but we see it in snapshots as well. We can see that the simulation images share the primary features, as we discussed yesterday in Alex's talk, of this equatorial emission model from Graulich, Saska, and Moroni, and we're able to reproduce the simulation images with these equatorial type models, including this, this horizon feature, which in the simulation is filled in with a finite floor, whereas in the analytic model has a exactly zero emission. And one thing that's particularly nice about this is that this feature is something that's visible at 86 gigahertz as well as 230 gigahertz. So the 230 gigahertz emission, we see the photon ring because we have limited optical depth at 86 gigahertz. That photon ring is blurred out by optical depth. But because this horizon feature is not actually dependent on having limited optical depth, as long as we don't have something blocking it along the line of sight, because it's really just a geometrical effect of the emission truncating at the horizon. You can see it at 86 gigahertz as well. And actually, we saw that earlier in the spectral index map, where we could see that the spectral index of the disk emission around the black hole was quite different than what we see inside this lens horizon, which is coming from just the jet emission along the lens. So I guess the last thing I'll mention is this is something that we can hope to observe with ngEHT. So this is a series of emission profiles now extended to log space, similar to what was seen in Alex's talk yesterday, where we see, as we get close to the black hole, we see the n=1, n=2 photon ring. But then as we go into the interior of the ring, the emission plunges in dynamic range and to these exact radii determined by the lens horizon. And so this is given again a finite floor in the simulation because of jet emission in front of the black hole that fills in the brightness inside this region. And critically, at least in this simulation, this floor is well below what we might see with eHT 2017. The dynamic range is just so limited. But if we extend to ngEHT dynamic ranges, we might be able to pull out this floor and observe this lens horizon feature directly. And so this is just a series of image reconstructions showing the blurred simulation here on the left, a characteristic eHT 2017 reconstruction where we see we can't resolve this feature, and a characteristic ngEHT reconstruction we see we can. So that's the end of my talk. Let me know if you have any questions. So my main takeaways are here. And thank you for your time.
Thank you very much, Andrew. There's really no time for questions, but if somebody has a quick one, I don't see any raised hands. So if you have questions to Andrew, I suggest that you ask them in chat window or on Slack channel. And right now, I propose to move on to the next talk, the next speaker. So our next speaker is George Wong from University of Illinois, and he will tell us about mass loading the jets. Go ahead, George.
Okay, can you hear me and see my
yes.
title slide? Great.
Yes.
Great. Okay, so first of all, I want to thank the coordinators for inviting me. I've had a great time. I think there's been a lot of great talks. I'm at a disadvantage now because both Sasha and Andrew presented a lot of the background information, but I'm also at an advantage for that, obviously. Okay, so I want to start my presentation by kind of remembering that, of course, we're all here at an ngEHT meeting, and one of the things that we want to hopefully come out of this meeting with is an idea of the science goals of the ngEHT, or what those goals could be. And so from my perspective, one of the things that I'm really interested in is really being able to probe this connection between black holes and jets. So obviously, we have this really long, really large, and really long-lived jet that we observe in M87, and just to remind everyone, right, we're talking about really, really drastically different scales between the arc second scale well, multiple arc-second scale of the jet features that we see, and the micro arc-second scale of the actual horizon of the black hole itself. And so we've heard about how this connection can occur many, many times, but I want to again briefly recapitulate the ideas. One of the leading theories for how this connection plays out, the connection between the black hole and the jet, is this Blandford-Dynamic mechanism. And the idea here is that if you have a magnetized plasma, so as Sasha said, if you have a highly conducting magnetized plasma, then as your plasma accretes, as the plasma falls onto the black hole, it pulls the magnetic field lines with it, because the magnetic field lines are frozen into the plasma because of charge realignment timescales. And so if you have black holes that are spinning, so the black holes are spinning, they start to drag space-time with them, the plasma is falling onto the black hole at the same time, the magnetic field lines that are being advected down to the horizon, along with the plasma, start to get wound up around the black hole. They're dragged with space-time, and so they end up being wound up around the axis, the spin axis of the black hole. And this kind of collimation of magnetic field lines, twisting of magnetic field lines, produces a pointing flux that ultimately can end up producing a very large power. And theoretical models show that this power that you would get from this pointing flux via the Blandford-Dynamic mechanism is approximately the right scale, for example, for M87 systems. And so again, going back to the science question, I think that one of the things that would be really great for the ngEHT would be to somehow actually observe or measure this Blandford-Dynamic mechanism's operation, or come up with evidence for it not operating. And of course, we can ask the question that I think Avery brought up maybe yesterday: what does it mean to measure? But I think that at the very least, from a practical standpoint, in order to make a measurement of the Blandford-Dynamic mechanism, you need to do at least two things. You need to have some kind of idea of what the spin of the black hole is, because if you have a non-spinning black hole, then the Blandford-Dynamic mechanism is not going to operate. And you also need to have some kind of measure of what's going on with the magnetic field lines in, for example, in the jet region, near the jet region, or just down at the level of the horizon. And so the way that we've kind of thought about this process, or at least from a simulation perspective, is in terms of this forward process, where you keep on adding different features into your simulations, into your models. And so you start with a fluid simulation that describes the state of the plasma and the evolution of the plasma as a function of space. And then you add on some electron thermodynamics models. And of course, as Andrew kind of briefly hinted at, you can build your electron thermodynamics models into your fluid simulations and so on. And then after you have some description of how hot the leptons are in your simulation, you can then perform radiative transfer and get images out the other side. But I want to remind everyone that really the process that we want to be doing is for ngEHT and for all these kinds of studies is kind of the opposite. So we want to start from the right-hand side and go to the left-hand side, somehow invert. It's a parameter inversion process. And this is really hard for a variety of reasons. Not only because if you count the degrees of freedom of the system, you have very few degrees of freedom, or you have many more degrees of freedom in your underlying system than what you're measuring, the number of data points that you're measuring. And of course, you can improve this ratio by considering things like polarization, considering things like time dependence, and just increasing the resolution of your simulation, adding multiple different frequencies. But this is, in general, it's a hard problem, understanding kind of what the emission source looks like just from the image. But it's not an impossible problem. And so since we have these simulations, since we have these fluid simulations, we can kind of look at everything from the reverse perspective and say, well, we have these simulations. What is the emissivity profile? Can we somehow associate the emissivity profiles that we see in our simulations to features in the images? And so I want to point out that if we want to measure the difference between, for example, mad states and sane states, well, in fact, mad accretion states and sane accretion states look very different in terms of emissivity. Mad states have a lot of emission in the funnel, and sane states don't, for a variety of reasons. And you can, again, having the benefit of all of the knowledge that you get from the simulations, you can then kind of decompose the image of emission from the jet into, you can map that into the image plane, and you can look at and see how different images that you would eventually measure map back to these different regions. And so I've just blown up those, that schematic cartoon at the bottom into these 3 rows, so it's a little bit easier to see. But one of the pictures that you might get out of this, this kind of analysis is that, if you have emission that's coming from the funnel region, you end up with these kind of sharper features that are kind of highly redshifted, highly beamed towards you. And if you have these disk features, you get this more diffuse intensity across your entire image. And then, in addition to just looking at different models, you can also say, okay, well, if you look at different frequencies, are you probing different parts of the flow? So, maybe if you're looking at the 230 gigahertz image for a particular MAD model, you might only see the funnel. But if you then go to different frequencies, you'll start to see the disk region and so on. Anyway, all of this is to set up the question that I think is perhaps one of the most important questions to answer, and that something that Sasha talked a lot about, which is, where does the matter in the jet come from? So evidently, in a lot of different maps, in a lot of different images, the emission that is producing a lot of the features in the image comes from this jet funnel region. And so where does it come from? And in this talk, I just want to briefly kind of overview 2 of the different processes by which you can end up getting matter into the jet, by which you can mass load the jet. And the first is this electron-positron pair creation that Sasha talked about. And the second will be matter entrainment directly from the disk into the jet. So I'll start with the electron-positron pair creation. And as Sasha mentioned, right, there are multiple different channels for how this can happen. There are broadly 2 different channels for how electron-positron pair creation can happen. Broadly, we call these different channels gaps versus drizzle. And so I will recap Sasha's really great original slides, initial slides in his presentation. And just remind everyone that here we're talking about the Bright-Wheeler process. So you can have an electron-positron pair that's created when you have 2 high-energy photons that collide with each other, that interact with each other. And of course, one of the criteria for this pair production event to happen is that you need the total rest mass energy of the photons to exceed, or sorry, you need the total energy of the photons to exceed the rest mass energy of the electron-positron pair. So if you plot the cross-section as a function of the center of momentum energy of your photons, of course, you have some lower level cutoff. So as Sasha said, this kind of raises the question, well, okay, sure, you have some overall bottom cutoff for when pair creation can happen based on the energies of the photons. But that still gives you some freedom in choosing what the energy of each individual photon is. And so you can have a high frequency photon and a low frequency photon that interact with each other and produce a pair cascade. As Sasha said, this pair cascade happens just because you have some low charge region. And if you have a low charge region, that means that you can't necessarily screen electric fields. So charged particles, when they enter this non-screened region, would be accelerated. And if you have strongly accelerated leptons, they're radiated high energies. And so these high energy photons will interact with the background radiation field, and the overall center of momentum energy of the system, of the 2-photon system, will be enough to pair produce. And at least in the context of black holes, this kind of idea, this pair cascade model was first proposed by Beskin in 1992. But you have this alternative model, which is what I'm going to briefly describe, which is this pair drizzle model, where instead of having a really high energy photon interacting with the lower energy photon from the background radiation field, you have two photons that are approximately MeV, approximately near the pair production threshold, and they can interact. And since you're not relying on these regions with unscreened electric fields, that means that you don't have necessarily as much of a sharp behavior, and you're not also a sharp behavior in time, and you're not also beholden to having regions where you have low charge density. And so this idea was originally proposed by the chair of the session, so Monica Mashkrashka, in 2011. So as I said, I'm going to talk about the pair drizzle model. And actually, let me go back here. And so one of the things that Sasha brought up, and I completely agree with, is that whether or not the pair drizzle model, so again, pair drizzle being two photons that are from the background radiation field, there's no really large acceleration due to unscreened electric fields. Whether or not the pair drizzle model actually operates is strongly dependent on the nature of your background radiation field, especially the high energy component of your background radiation field. So just for reference, photons, in order to have the appropriate rest mass energy, photons have to have approximately 10 to the 21 hertz, so the frequency has to be approximately 10 to the 21 hertz. And so you see that, in certain models, you certainly have a high energy component of your spectrum there that can produce these pairs through this pair drizzle process. But often this high energy component is produced by regions where we don't necessarily have the best understanding of the electron thermodynamics. So everything that I'm about to say, of course, should be considered through the lens of the uncertainties in the electron thermodynamics of our GRMHD simulations. That having been said, if you just do some calculations from radiation simulation, so Andrew mentioned these radiation simulations from Ben Ryan. So we took these radiation simulations from Ben Ryan, and of course radiation simulations have a full description of the radiation field over the entire domain. And so you can directly do the calculation. You can directly measure at every point in space what is the distribution function of the radiation field, effectively of the photons, and evaluate the pair production rate in all different locations. And the upshot of this entire calculation can be summarized by answering the question whether or not, if you evaluate the pair production rate, again, this drizzle pair production rate due to the high energy component of the background radiation field, if you evaluate this pair production rate in the funnel or in the jet, so over here, are there enough pairs that are produced through this pair drizzle process to screen the electric field? So again, going back to this dichotomy between pair cascades and pair drizzle, pair cascades only operate if you have unscreened electric field. So in principle, if you have pair drizzle, if you have a strong enough pair drizzle, you can produce enough charges to completely stop the pair cascade process. And so with all of the caveats that were described before, what we find is that in fact, as you increase your mass accretion rate, or as you increase the mass of the black hole, it becomes harder and harder to actually open up these gaps. So the pair drizzle process operates. It doesn't produce a very large amount of pairs, and it certainly doesn't produce enough pairs to explain the overall energy or the mass content of the jet necessarily. But it does produce enough pairs. It does produce enough charge to screen the pair cascades. And so over on the right here, I'm just showing you a set of models that we ran and a rough scaling relation that we plotted, showing that for M87-like systems, and so this paper was published before the EHT results, so we allowed some uncertainty in m-dot and also in the mass of the black hole, which is what you're seeing on the vertical axis. In M87-like systems, we don't actually believe that pair cascades can occur. And so this raises the question then, a science question that the EHT, that the ngEHT can answer, is the jet actually populated by pairs? And if so, what is their source, if not pair cascades? All right. So that's the first question, or the first method that you can use to mass load the jet. And the second one it has nothing to do with pair creation or pair cascades. It's just directly entraining matter from the disk into the jet. And so I'll flash a brief slide now on kind of the anatomy of an accretion flow. And so the picture that you should have, again, for these highly conducting plasmas, which certainly is an operative assumption, a valid, more or less valid operative assumption in the high density disk region. The plasma will flow along the magnetic field lines. Again, the magnetic field lines are frozen into the plasma, so as the plasma affects it, it has to follow the magnetic field lines. And if you just plot naively the magnetic field lines throughout the simulation, you find that the jet region and the disk region are magnetically disconnected. So if plasma is indeed required to flow only along magnetic field lines, then it's not obvious how you can get matter from the disk region into the jet region, because you'd have to violate this condition that plasma wants to flow along the magnetic field lines. So what we found, or what you find if you look at simulations, is that, in fact, this nice picture that I think people are often want to assume about black hole accretion systems, of there being a kind of nice steady flow of matter from the disk at large radius down to the event horizon, it is more complicated, especially in mad flows. So there's this interface layer between the disk region, which here I'm plotting in blue, and the jet region that I'm plotting in red. This interface is potentially unstable, and in particular, it's potentially unstable to shearing instabilities, because you have a lot of matter that is in the disk region that is falling onto the black hole with a relatively slow velocity that's set by, just infall processes and also potentially magnetic torques. But then you also have this other evacuated jet region whose angular velocity is more or less entirely set by the spin of the black hole. So again, if the Blandford-Denard process is operating, you have these magnetic field lines that are being twisted by the hole, and so they're pulling the plasma along with it. So you can then ask the question, well, if you do some kind of a linear analysis of the shear layer between the disk region and the jet region, should this be unstable? And the answer to that is that yes, in principle, it definitely can be unstable. The boundary layer is unstable to the magnetic version of the Kelvin-Helmholtz instability. The basic upshot of the linear analysis is that if you have magnetic field lines that are, or if the magnetic field is anti-parallel or parallel in the region across the interface, so in other words, parallel or anti-parallel connecting the jet region on one side, the jet region, and on the other side, the disk region, then your instability can operate. And you might then say, okay, so this is nice, this is a nice linear analysis, but do you actually see it in the simulations? And the answer to this question is yes, we do see it in the simulations. And so here I'm just plotting, I think it's probably skipping for you because it's skipping for me, but we're just showing the flow of density going around the hole in one direction in the midplane, and then in the other direction along the pole. And if you take two particular time slices in your simulation, you actually can see directly the formation of one of these Kelvin-Helmholtz rolls. And we'll come back to this in a second. But I want to point out now very briefly that this kind of analysis also allows you to do a kind of study into what the profile of the jet is in certain simulations. So it's easiest to do this kind of study considering retrograde systems, because in retrograde systems, it's very clear which region you should call the jet versus which region you should call the disk, because you can just directly measure the angular momentum and say, okay, is the angular momentum aligned with the hole or is it aligned with the disk? And so that gives you a nice way to kind of differentiate between the jet region and the disk region. And so I'll just briefly describe some of the results that we see from doing this kind of study. So the first is that perhaps unsurprisingly, the same simulations have a more narrow and defined boundary layer compared to the MAD simulations. And you can understand this, I think, from the perspective of remembering that MAD accretion is very choppy, MAD accretion is very hectic. So you don't have, rather, sorry, I'll say, so you will have a lot of kind of stray features in your MAD accretion that that kind of spread out. You have a lot of wildly flailing plasma tendrils. So the overall transition between parts of the accretion that are nicely falling onto the hole and thus have this blue angular momentum, and the parts of the accretion, or parts of the system rather, that have the opposite sign of angular momentum going out with the hole, kind of varies wildly with time, and so it broadens out that interface profile. And so you can do your standard things like fit the funnel profile with a parabolic model. And so I'm just pointing out that what we found was that things have, x to the 1.8, so where x here is going horizontally and z is going vertically. One thing I want to point out is that we only did this analysis within about 20 m of the hole. I think that I think it's certainly a very interesting question to ask what's going on at large distances, but I think that any kind of analysis there is subject to questions about what your initialization, what kind of initialization you use. Is there, because you certainly don't have enough time to equilibrate things at very large distances, so 100 or 1000 RG. So the profile of the jet that you end up measuring from your simulation will be dependent on your initial conditions to some extent. But I know that Koshik has thought a lot about this, and so I'm going to advertise his talk later today. Anyway, so the last thing that I'll talk about in this analysis is just that if you think back to that instability, you can kind of try and measure that instability. In the sense of you can try and identify how much of the matter that is falling onto your black hole from large distances, how much of that matter actually ends up falling onto the black hole versus how much of the matter gets entrained into the jet. And there are a lot of caveats and little details that you have to think about here, one of which is this floor treatment that Sasha mentioned in his talk as a reason to perhaps distrust GRMHD simulations. And again, I agree broadly with the idea. So you can't just go in and measure how much mass is flowing out of the jet. That doesn't work because you may be dominated by floors. And Monica, this is my second to last slide. So
okay, 1 more minute.
Yep. It's challenging. You can't just measure the mass flux, for example, through a cap region in the jet because you may be dominated by floors. And so in order to actually understand this mass entrainment rate, we did a tracer particle analysis where you just produced a whole bunch of tracer particles that are passively affected along with the flow. And you just count literally the number of tracer particles that fall onto the hole, and you can compare that to the number of tracer particles that get entrained into the jet and shoot out to infinity. And this, of course, is not going to be subject to your treatment of the floors because you're not injecting new tracers every single time you apply the floors. And so what we found for this particular case study is that the mass entrainment rate is actually pretty appreciable. It can be on the order of 1%. And so this is another possible way that you can get mass into the jet. Of course, this is a very different kind of matter. So here you're actually pulling in ions and electrons as opposed to a paraplasma. And so this will have different observational signatures. And so I want to point out that the science question here, or one of the science questions you can ask is can we actually observe this entrainment? And one of the things that Chet mentioned, I think a few days ago, was that we might be able to, with high enough resolution, actually track the trajectories of infalling matter. And so could we also potentially track the trajectories of matter as it's entrained into the jet, or once it enters the jet, and as it gets shot out along the jet? Can we see these things? And I think that these are really interesting questions because I think what you've heard from many people's talks and what you will continue to hear is that there is there are some disagreements about what's actually going on in these systems, and what better way to identify or to better probe these disagreements than to than to have observational data. And so I won't read through this, but I'll leave it up as a kind of summary slide. These are some future directions for science goals. Thank you for listening.
Thank you very much for your talk, George. That was wonderful. May I just ask a quick question about paired results, because I have computed that like a decade ago.
Yes.
I was wondering if your library of paired result models contain any MAD simulations.
That's a great question. No is the short answer. The longer answer is we've looked at it kind of. But not published and not to any level that I would be confident, publicly vouching for the results yet.
Okay, thank you very much. Ramesh?
Yeah, so George, thank you very much. That was a nice talk. I have a very kind of simple, binary question.
Mm-hmm.
So Andrew said in his talk that MAD systems radiate more from the equatorial plane,
mm-hmm.
and sane radiate more from the funnel.
Mm-hmm.
And he cited paper 5, and I looked at paper 5, and I think that is correct. But I think in your talk, you said just the opposite. Did I hear that wrong?
So let's see if I can pull up that figure 4, as it's called in my head. I think it. I am very comfortable with the statement that you will see the funnel wall more, or that you will see stronger funnel wall effects in MAD simulations than in sane simulations. I think that this is kind of strongly dependent on your model for the electron temperature. But I'm very comfortable saying that, so for this middle picture here, you don't see things that look like this in MAD simulations.
Okay, so this is actually in some sense contrary to what you could see directly in the picture in paper 5.
So let me bring up that picture. I think that so this 3D rendering is perhaps misleading because there's a strong amount of emission here close in at close radii. Sorry, I'm trying to bring up figure 4. I see. So they're talking about this.
Yeah.
Okay, so that is, yes, okay. I will say that in order to get structures that look like, let's see if I can try and bring this up. Right, so this is very different than these 3 features here. So this, for example, or this will end up looking something like this in your 3D representation. So, if you're, yeah, Kaushik is responding, that you can get higher electron temperatures in MAD jet sheets overall, so it is dependent on the electron temperature prescription. But I think that the pointed answer to your question, Ramesh, is that I would call all of these pretty similar, right? So if you wanted to plot this center panel in this representation, you would see a giant blob of emission out here. So here you can kind of describe it. You can break up the emission here into some kind of compact core and some fuzzy region. So that's what you're seeing here in these MAD models. You're seeing a fuzzy core here, and you have some kind of hot matter that's corresponding to higher temperatures, at least in our model, for the region where you're interacting between the jet region and the disk region. I really think that it's incredibly unlikely that in any MAD model, and actually I've never seen it in any MAD model, that you get this really extended disk emission feature. And you can see this in another paper, or sorry, not another paper, in another figure in the same paper. So these are the same GRMHD simulations, and you can contrast those with MAD simulations. And so if you really want some extended disk emission, you only see these in the same case. And as Daniel pointed out, this is an R-high-1 model. But you don't ever see, at least in any models that I've looked at, and certainly that were in the library, you don't ever see this kind of disk feature that you see in the same cases. You don't ever see it also in the MAD cases.
Great, thank you.
Okay, thank you very much, George. Unfortunately, there is no more time for questions. So, Sasha, I'm sorry, could you ask your questions maybe during the coffee break? At this time, the session is over. Thank you very much to all this. And thanks everyone for your attendance and your questions. And now I guess it's time for coffee break, and I will give it over to LOC.